I'll be exploring the dynamic interplay of rock and water at the heart of water worlds. My name is Tanja Kovacevic. I'm a PhD candidate in Burkhard Mellitzer's group, and we are located in the Department of Earth and Planetary Science. So just very quickly, I'd like to thank my collaborators and Burkhard and Felipe for this paper. It's open access on science, so you can go ahead and check it out. Today, I'll just start with a quick outline of my talk. I'm going to start with the background, go over some DFT molecular dynamics, go through giant impacts, and then finally I'll summarize all of the work. So let's begin with the background. This little ribbon at the top is going to let us know where we are in my talk. So we've discovered now well over 5,000 exoplanets in our galaxy. So it's a super exciting time for me to jump into becoming a planetary scientist. Even while we're discovering all these exoplanets, back in 2017, Fulton et al. Went and took the distribution of certain exoplanets that were pretty close to the host star and just plotted them based on their size. And we can see that there's this bimodal distribution, which means seems like there's two types of exoplanets. Again, within a certain range. So the range is going to be from 1 Earth radii, somewhere above, right about where Neptune is. And a lot of people in astronomy, physics, planetary sciences, we love our very intricate names. So we're going to name these planets super-Earths and sub-Neptunes because they fit right in between Earth and Neptune sizes. I think it skipped over a slide. No, it did. Okay. So then we further refine these because, we have super-Earths, sub-Neptunes. That doesn't really tell us what these planets are made of. We don't really even know what's inside Uranus and Neptune. So Zhang very recently, and others, did this very complicated, beautiful plot if you take the time to read it, but I want to focus on what's in this circled area. So a lot of planetary scientists, we like our equations of state, so let's follow this red line here. We're going to have mass on the x-axis and radius on the y-axis, and this red line is pretty much going to show what if my planet was made 100% out of iron. Now, what I've circled here are planets that kind of hug this cyan blue color, which would mean that these planets have a lot of water on them. So, based on the title of my talk, that was exciting. We're like, yes, cool. There's other people that, aren't just astronomers that are also kind of considering these things and thinking that water worlds exist. So ultimately, Zhang put a category of water worlds where we're going to have planets of rock and icy compositions that range between 2 to 4 Earth radii. Then Luke, which came a couple months after, published another article talking about water worlds, and instead of looking at mass and radius, now we're going to look at mass and density, because again, we're going to look at this area here. That's going to give us more evidence that at least theoretical evidence that there are water worlds that exist because, sometimes you can interchange whether you have a rocky planet with a huge hydrogen-helium envelope or a water world. So a rocky, inner part and then a large water layer over top. So this kind of gives us a little more evidence that there are water worlds based on density. Let me define what we mean by water world before I get into it. So they're going to be planets of rocky and icy composition without a significant atmosphere. So here's an example of a water world I have. It's going to have an iron core, a rocky mantle, and this huge water layer overlaid. Now this makes a lot of assumptions about the state of the planet, that it's fully differentiated, so its layers are all separate. That's going to have some baked in assumptions about how the planet formed, what state it's in terms of its heat release, so we're going to investigate that a little bit. So other people have investigated the implications of maybe the rock and ice maybe mixing at the rock-ice boundary. And what I mean by rock-ice boundary is you're going to have this rocky core, and then there's going to be this huge water layer, so this is the rock-ice boundary. So Alana Bazan in 2022 made a call to this right when I was working on this project. So that was really cool to see that water worlds were starting to make a little bit more of an appearance in the literature. And then I even saw, if we don't even particularly look at water worlds, if we consider magma ocean planets, there has been work done too, where if we consider these magma ocean planet just means rocky planet that's super hot, so it's all magma. What if there's water hidden inside the magma? What can that do to its mass and radius? So there's a lot of people that have been investigating water incorporation into these rocky planets, and that maybe a planet didn't start off completely differentiated. Maybe there was some more dynamics where the planet can be in different states depending on when we're looking at it. So my big question is, again, at this rock-ice boundary layer, are rock and ice miscible at the rock-ice boundary layer deep within a water world? So that's our main question. And then by miscible, I'm just going to use that term pretty frequently. It just means the homogeneous mixing of two substances. So I might say mixing, I might say miscible. They're going to mean the same thing to me. So first, we're going to choose our material of interest. Before we even get started, we're going to consider a very prominent rocky composition that we find within Earth. So it's going to be MgSiO3, or enstatite, or the high-pressure version, bridgmanite, which is what we're investigating here. And then water worlds, we're going to look at water ice. And then these are going to be the conditions I'm interested in. So we looked at that paper that I showed earlier with Fulton, where we have that bimodal distribution. So we looked at planets that ranged in those like mass and radius sizes, and we found our conditions of interest were going to be pressures of 30 to 200 GPa. So GPa is like, I think 4 orders of magnitude larger than what we find like here on Earth. So like a ton of pressure. And then we're going to investigate temperatures from 0 to 8,000 Kelvin. And the reason we chose 8,000 was we just wanted all the materials to melt. We wanted to see if there was maybe mixing before they melted, some high pressure phases that led to different dynamics, or if the melt would remain separate or if it would mix. Again, I'm not like the only one looking at rock-ice mixtures. There have been other high-pressure phases found. So relative to the work we're looking at here, this is going to be relatively low-pressure phases, even though these are still high pressures. Again, compared to our conditions of interest, we have some low-pressure phases of these hydrated magnesium silicates. So that means like this MgSiO3 and H2O are incorporated into like one crystal. And then we're going to have another super high, or they called it ultra high, magnesium silicate phase that, again, it's found at way higher pressures. But again, it's really interesting just tying all these together, going from the low pressure to high pressure. And again, luckily for us, in these conditions, the MgSiO3 and H2O actually like dissociate into 2 separate crystals. So again, we're going to start with these 2 separate and just see what happens, and not consider high pressure phases. So our approach is going to be a heat until it mixes approach. We're going to build our rock ice supercells. So we're going to have our rocky material down here and our water material above, and then all the atoms are colored as such. All the oxygens are same in this system. I just colored them separately so we could kind of easily differentiate between rock and ice. So I'm going to run density functional theory and molecular dynamics. That's just using density functional theory. It gives us the quantum mechanical accuracy to investigate these high pressures and temperatures, because we can't experimentally, it's still very difficult to run these experiments. So right now, while we're still, we have the computer power finally to investigate these conditions, we're going to use them. So I'm going to use molecular dynamics and computer models to see whether rock and ice mix. So we'll start by building each system. So this one that I've like specifically visualized here is going to be this 120 GPa. And then we're going to incrementally heat up the system. So each box represents a simulation that we do, and that's going to provide an isochore. So as I heat up the system, because the volume is staying constant, the pressure is going to increase, and we're going to get this like slope effect. So after countless hours, I ran all the isochores. So here are all our isochores. We see that these aren't perfect lines, which is interesting because that gives us a little insight into the thermodynamics, that there's something happening, like maybe phase changes, or there's something going on because it's not perfectly straight. There are little kinks in the curve, so now we have to investigate. So once I run all these simulations, we have to post-process them, and we do them in 2 pretty simple ways. We're going to look at the mean square displacement, which tells us how much an atomic species diffuses throughout the trajectory. And then we can also look at the radial distribution function, or you might have heard the term pair correlation function. They mean the same thing. It's the probability of finding a particle at a distance r from another particle. So for the brevity of this presentation, we'll just look at the MSD. So it's pretty much just watching how the atoms move and then averaging them over like an atomic species. And then to be even a little more specific, because we're looking at mixing, MSD gives us an idea of diffusing. If we decompose that mean square displacement just in the z direction or perpendicular to this interface, that might give us a hint about which simulations to investigate more where we're seeing potential mixing happening. So first, we're going to walk through the MSDs, but let's click into the same page of how to interpret MSDs. So here we have an MSD plot. Each line is going to correspond to the atomic species. So they're going to try, I'm trying to match all the colors here, so we're not doing too much thinking. On the x-axis of these plots, we're going to have time. And then on the y-axis, we're going to have MSD. So we're going to consider if we see a plot that looks like this, where all the lines either go straight or we don't see them, we have to like kind of squint to see it. That's going to indicate to us that these atoms are just vibrating around their lattice points, they're solid. If the MSD is increasing over time, that's going to indicate to us diffusing and then mixing, with the caveat that we're looking in that z direction. So it's not going to give us a for sure sign that it's mixing, but again, it can just help us when we're doing the radial distribution functions where to look and where to really investigate, or which simulations to investigate. Okay, so the plot that I just showed you with the green dots now has a bunch of other dots and colors and shapes. So right now we're not going to worry about that. I'll go through that in a second. We're going to show, right now I just want our eyes to go to, there's blue points and there's red points. Red is going to mean mixed, while the blue is going to mean not mixed. So cool, we found mixing. But let's quickly go through what all the other points mean just because it's fun. So here, all the hexagon points, are the ones that I've kind of highlighted in green, are going to indicate where rock is solid and ice remains solid. Then we're going to enter our first exciting high phase of superionic ice, pretty much. So that's going to mean rock is still solid, ice is superionic. Superionic pretty much means where the oxygens stay put in the H2O, and now the hydrogens are diffusing freely, almost like water throughout this oxygen lattice. And it was really interesting because we didn't see mixing here. We were curious how rock and the superionic ice would almost like what their dynamics were. So we didn't see any mixing, we didn't see any protons shooting up into the rock. Then we have rock still remaining solid and ice is now melted. So this is going to be an ionic ice. This isn't H2O water that you see every day. This is going to be like a slurry of like hydrogen ions and oxygen ions just flowing in this it's called ionic water. There's a couple words, but I'm not particularly sure the exact terms, but I like to call it ionic water. And then finally, we're going to get rock and ice mixing. So we see that, again, all those MSD plots, the lines are all increasing with time, so that was kind of our indication initially when we were looking at the simulations that there was mixing. Also, another really easy way is just to show you what we mean by mixing. So this is just a visualization of the trajectory. We started off with rock at the bottom, ice at the top, and I think as this trajectory goes on, I don't know if any of y'all can tell me where there's rock or where there's ice. It kind of is like this mixed slurry. So yeah, that's what we mean by mixing, and yeah, this will happen in equilibrium. So these are ultimately the results from our DFT MD simulations. Here I've just plotted the melting curves for H2O and for MgSiO3, and this is an experimental curve for MgSiO3. It came out like while I was doing this research, so like it was beautiful because when we laid that melting curve right on top where we saw miscibility, I feel like we can all see kind of a trend here, and the trend is that once rock melts, rock and water become fully miscible. Okay, cool. So we know that they're miscible, but what does that mean about water worlds? Like, are these pressures? Well, the pressures are going to be, at least what we've modeled, are going to be present, but are the temperatures present at that rock-ice boundary layer? Okay, let's talk about giant impacts and where we might get that temperature. So let's just preface really quick to impact simulations before we just jump right in. So we can consider, various astronomers consider different types of planetary growth, but here we're just going to consider collisional growth of planets. So this is how you might imagine a solar system forms, and we are going to just focus right in on that region of solar system formation where, again, I said collisional growth, so we're going to have planetesimals just like banging into each other and making larger planets. And here I have an image of that, a cool one I found on Google. Yeah, so we're going to look at ice-rich bodies just banging into each other and seeing if the temperatures can get hot enough for rock-ice mixing. So we collaborated with Sarah Stewart at UC Davis. She ran smooth particle hydrodynamics, where she ran simulations on impacting water worlds. So I just put here a summary of all the initial conditions. She ran like a ton of giant impact simulations. So here we looked at planets with a mass of 70% to over 400 times Earth's mass. 400%. 0.7 Earth masses to 4.68 Earth masses. Don't do quick math in your head. The weight of water on these planets is going to range anywhere between 15 to 44%. So like, imagine the whole Earth covered in water and like a giant layer of water. And then we're going to look at radii anywhere between 1 to about 2 Earth radii. And then for this example, we're looking at the end members. And here's a super cool simulation of planets colliding. So this is going to be a graze and merge, where the planets, pretty much, these planetesimals form one larger planet. And we're going to look at this boundary right here. In these simulations, each point has its own thermodynamic properties for the material, so we can actually just look at these points in here and say, hey, like, how hot is it in there? So yeah, pretty much what these impacts give us are the pressures and temperatures necessary for mixing. We can kind of investigate that, theoretically, of course, and then an estimate of how much rock is mixed up into the water layer. So from all of those initial conditions, we got almost ubiquitously in the simulations, anywhere from 6 to 22% of rock is going to be mechanically mixed up into that water layer. So that's super exciting because our main conclusion that we were able to draw was that, two. Once rock melts, rock and water become completely miscible, and then once we pair that with the impact simulations, we're able to provide theoretical evidence that many water-rich exoplanets have mixed mantles. So we just want to update that figure I showed before, where instead of 3 layers, now we have 4 layers, and we're incorporating this mixed mantle into that interior profile. And thank you. So these are all the contributors and all the people I've collaborated with and have wonderful conversations with about my project. And if you have any questions, feel free to email me.